Okay, so welcome back to this 10th lecture of biomems, and just to review what we were talking in the last lecture, we tried to generate an equation wherein the free energy per mole of the system which is also expressed as kT ln gamma I being the activity coefficient, was equated to the total amount of work that was needed to bring a charge ZIE into the minus ZIE into the central ion of interest, which is a plus ZIE charge. In other words, in order to give a charge its counter ionic cloud, the amount of work which is done is given by this integral of dW. So from the equation we try to get an expression in terms of gamma I as the following. Okay, so ln gamma I, excuse me, natural log of gamma I, the activity coefficient, also came equivalent to minus Zi square epsilon square by twice d kT into the counter ionic radius k by 1 plus small k times of A. A here was the ion size parameter. It is an indication of tentatively what is the size of the central ion of interest. Okay. So also we know that k essentially is nothing but 4 pi by d E square by kT sigma Ni Zi square to the power of half. In other words, we can express this in a more appropriate manner by assuming that what is really Ni. Okay. Ni is essentially the number of moles of different charges, okay, whether it is positive or negative, as different charges. You remember the way we talked about the subscript I in our lectures before, per unit volume on the point A. Okay, on the point A, we were talking about a central ion and a point A which was close by where the potential was phi, and then a negative ion atmosphere which was all the way around it, just for recapitulating what we had done earlier. Okay. So this was the point A essentially. This here, give me a minute, was the point A, and which was at a distance of small a from the center of this charge. Okay. This was the point A, and the radius here is small a. So we can really express this in terms of the concentration of the various ions that are there in the solution, and from which we formulated the mean concentration. Okay. So what we tried to estimate this as, since Ci is also in terms of molar or moles per liter, and this Ni was per centimeter cube, because it was all CGS units which were used at the beginning of the 19th century to explain at least problems, a majority of the problems in this chemistry, or related to charge essentially in chemistry. So here we could consider the number of moles per unit volume Ni to be a product of the Avogadro number n, which is 6.023 into 10 to the power 23, the numbers in 1 mole, divide into the concentration Ci by 1000 cc or 1000 centimeter cube makes 1 liter. So from these two, from this kind of an expression, the K could be written as really 8 pi by d epsilon square by kT n by 1000, okay, half Ci Zi square, and this is nothing but the mean ion concentration of I. Okay, so we can call it mu I. So, we would today try to go ahead in this and try to find out what this ln gamma I would be in terms of this final and full expression for k, and we get that ln gamma I, and now I would like to change the subscript I by its essence. The way that we had started all these things, we had assumed I could be either positive or it could be negative. Okay, so I write gamma plus minus here is equal to minus epsilon square by 2d kt times of z plus z minus and modulus of that. So, for the principle of electroneutrality, the positive and negative charges in otherwise electrically neutral medium would be equal, exactly opposite. So, even if we do the total amount of positive and total amount of negative charge, that would be same as reporting the square of the magnitude of the charge. Of course, you have to take the magnitude of z plus z minus times of k by 1 plus k into a, and k here comes out to be equal to 8 pi. Let me just go ahead and shift this down a little bit so that it will be convenient. So, this is z plus z minus mod times of k, which is 8 pi by d, right, epsilon square by kt n by 1000 times of, this is whole half of course, times of root of mu I divided by 1 plus the value of k again being 8 pi by d epsilon square by kt n by 1000, okay, whole half, excuse me, should be third bracket, second bracket, sorry, whole half times of root mu I times of a, where a is the ion size parameter. Okay. And this gives us a very interesting way of representation. We could couple this all together and just write it as in the following manner: z plus z minus, of course, modulus, and epsilon square is taken here, writing the value of 8 pi by d epsilon square by kt n by 1000 half root mu I, right, and in the denominator you have twice dkt plus twice dkt times of 8 pi by d e square by kt n by 1000 whole half root of mu I times of a. In other words, so therefore, we can write this expression as in a little different manner, so that it can be more simplified. So, you have minus log of gamma plus minus, right, and you can write this as z plus z minus a times of root mu, okay, divided by 1 plus b times of, so therefore, this can be represented as 1 plus b times of a times of root of mu. Okay. These a's and b's are just it is like for convenience, overall convenience, we can report these, and if you really represent the whole thing in terms of a, mind you, now there is a log here which is equal to 2.303 ln. Okay. So, 1 by 2.303 ln value. So, essentially a here is nothing but square of e by 2.303, and I am just simplifying and writing it down, which is convenient, by 2 pi n epsilon square by 1000 k3. This is just by simplification that you can represent this particular form with 1 plus b times a root mu, and here z I square times of a times of root of mu. Z I square is again modulus of z plus into z minus, right, times. So, this raised to the power of this raised to the power of half times of 1 by dt to the power of 3 by 2. That is how the A can be represented, and the B here in this equation can be represented as 8 pi n epsilon square by 1000 k, okay, times of 1 plus dt to the power half. Interestingly, if we put the values of the dielectric constant for water, in most of the cases the solutions which are being investigated is essentially an aqueous based solution of these ions. Okay. So, the basic medium there is water, the basic dielectric is water. So, if we put the value of the dielectric constant d of water in these expressions A and B, okay, simultaneously, and consider the experiment to be done at STP, experiment to be done at standard temperature pressure, you know. So, 298 Kelvin, 1 atmosphere pressure, this kind of a convention, this type of condition. And then of course, n's value is a universally acclaimed fixed value 6.023 10 to the power of 23 numbers, okay, of atoms or molecules or charges, as in this case, excuse me. So, therefore, we can calculate the values of A and B. If you look at and also the E here is 1.6 10 to the power of 19 minus 19 coulomb charge of 1 electron. So, the A it kind of encompasses all these constant values. You have a k value for the Boltzmann constant, you put the Boltzmann constant value, you have 1000 n, you have E square, and you have dielectric constant for water and temperature 298 Kelvin. So, you can compute all these values and it comes out to be 0.511 and B comes out to be 3.29 into 10 to the power of 7, a relatively very large value. Okay. But the very fact is that because this B is also in product with the ion size parameter, which may be a few nanometers, and we will be investigating and estimating a few tables later on for the ion size parameter A. So, therefore, the equation and the gamma value would hold consistency, okay, and therefore, the whole equation can really be written down in the terms of minus log gamma I, as you are seeing here, okay, equals A times of Zi square, Zi is being the positive or the negative charge, divided by 1 plus B A root of mu, where A is calculated to be 0.511, B is calculated to be 3.3 into 10 to the power 7 by assuming STP, standard temperature pressure, and the various parametric values for n, Avogadro number, epsilon, electronic charge, so on and so forth. Okay. So, the A is a very interesting proposition here, the A here, as you see in this particular, you know, area here, the A is the ion size parameter. Okay. So, it can be very well enlisted, and some standard ion size parameters are listed here. If you can see here, you know, selenium ions or tin ions of quadrivalent state has an ion size parameter of about approximately 1100 picometers. Similarly, you have you know, H plus, Al plus 3, Fe 3 plus and Cr minus, these values they have about 900 picometers, and so essentially these all ion size parameters have been investigated or evaluated from the Debye-Huckel theory, okay, and they are tabulated and they are used off and on for all sort of experiments. So, therefore, all the equations, all the parameters in this particular equation here for estimating the activity coefficient exist. You know what Zi square is, you can calculate what the mu I is, the activity coefficient of the you know the mean concentration of the particular solution is. You know what A and B are, these are constants which are estimated by the standard STP conditions, standard temperature pressure conditions, and therefore, ion size parameter, if we borrow it from this table, which has been probably estimated by experiments, can be used very well to calculate what is the activity of a particular ion of interest while you are doing the detection protocol. Having said that, let us actually look into a little bit of, you know, kind of solved example where we talk about how to calculate the activity of sodium and sulfate ions independently in a let us say 0.01 molar solution of sodium sulphate. So, you have a case where you have a sodium sulphate solution and you would like to find out the activity coefficient of sodium and sulphate ions independently or individually by looking at you know the Debye-Huckel set of equations. So, let us try to solve this. We have a case where we need to find out the activity given of the ionic strength of or given the molarity of the sodium sulphate solution. So, the ionic strength of the sodium sulphate of the 0.01 molar Na2 SO4 sodium sulphate solution is calculated as below. Okay. You have half CIZI square, right. How many i's are there? There is a Na plus and there is a SO4 minus 2. So, there are 2 i's. Okay. So, mu I in this case would be half of concentration of Na plus, which is essentially 0.02 molar. Okay. So, 2 into 0.01. The sodium sulphate solution has a molarity, mind you, of 0.01. Okay. So, there are 2 sodium ions every molecule of Na2CO4, and so therefore, you have the overall molarity of Na plus as 0.02 molar. Okay. So, the concentration times of the square on the valency, which is +1 in case of sodium, okay, plus, and this is essentially a summation term because it is a cumulative of all the positive and negative charges. So, now you have the concentration for SO4 which is only 1 molar or which is only 1 in the molecule. So, you have a concentration of 0.01 molar times of, now the charge here is -2, okay, because SO4 or sulphate ion is bivalent ion essentially, square of that. So, this comes out to be from calculations equal to 0.03 molar. So, this is the mean ionic strength of this sodium sulphate solution. So, once the mean ionic strength is calculated, rest of the things are easy. You just need to calculate minus log of gamma Na plus in this case, which would be equal to let us say the 0.511, the A term terms of times of the square of the valency on the sodium, which is +1 square, times of root over mu I, where mu I is 0.03 molar, and divided by 1 plus B, which in this case is 3.3 into 10 to the power of 7, times of the ion size parameter of Na plus, which can be obtained from the table as given before here, that the sodium Na plus essentially, if you look at this particular zone here, has an ion size parameter of about 400 picometers, okay, or 4 into 10 to the power of -10 meters, or 4 into 10 to the power of -8 centimeters. So, since we are actually using the CGS units for calculating everything here, we would take the ion size parameter A as 4 into 10 to the power of -8 centimeters times of root of 0.03 molar. Okay. So, this comes out to be equal to 0.0719. That is what the ionic strength of the log of negative log of the ionic activity of Na plus is. So, let us calculate do the same kind of calculation for the SO4 ion. So, in case of SO4, the activity can be, the equation can be written down as minus log gamma SO4 minus 2 equal to 0.511, that is the A parameter, A aspect, okay, the coefficient A, times of square on the valency, okay, of sulphate, and sulphate's valency is -2. So, square on -2 times of root over 0.03 molar divided by 1 plus the B constant, which is 3.3 10 to the power 7 times of the radius of SO4 ion, which again through this particular figure here. So, SO4 -2 and Na plus are more or less in the same size domain, it is about 400 picometers. So, essentially it means the ion size parameter A for SO4 -2 should be about 4 10 to the power -8 centimeters as before. Okay. Mind you, again this all these equations are in terms of CGS units. So, apart from the molarity, which is standard universal unit, the other equations other components of the equation has essentially CGS corresponding unit, centimeter gram second unit. So, this comes out to be 4 10 to the power -8 times of root of 0.03, and essentially that is calculated to be 0.2876. Okay. So, taking antilogs on the both equations solved earlier, the activity of the sodium ion comes out to be 0.847 and the activity of the sulphate ion, SO4 ion -2 in this case, comes out to be 0.516. Okay. So, if we look at these are the activity coefficients. Let me just reiterate, the activity coefficient of the sodium ion comes out to be 0.847 and the activity coefficient of the SO4 ion comes out to be 0.516. Now, if you want to look at really the activities of both the ions, which is also known as Na plus, and this A is probably the activity, do not confuse it with the ion size parameter. Let us just get a different name here for convenience sake. Let us say we have we just write acti instead of, or act Na plus, okay, equals gamma I times of Xi. As you know, Xi is the ionic concentration of the particular analyte. So, in case of sodium you have 0.847 as the gamma I, and the Xi, as you know in this case, because you have 2 atoms per molecule and the overall concentration is 0.01. So, for sodium the concentration is 0.02 molars. Okay. So, the activity in this case is only about 1.69 10 to the power of -2 molar, and in case of SO4 the activity SO4 -2 can be the gamma SO4 -2 times of concentration of SO4 -2, which is 0.516 from above times of 0.01 molar. Mind you, in one molecule there is only one SO4 atom which is present. So, therefore, its concentration is only same as that of the Na2SO4 solution. So, this comes out to be equal to 5.16 10 to the power of -3 molar. All right. So, that is how you are able to calculate the activity of Na plus and SO4 minus in a solution, in a sodium sulphate solution, by looking at the various aspects. Now, what I would be interested to look at here is that if you may just see that the activities of both are different. So, therefore, Na plus is a more active ion than SO4 minus. So, in such kind of situations, if there is a presence of both ions, that is Na plus and SO4 minus, there is a tendency of the electrode to be heavily interfered by the Na plus ion if you are detecting sulphate ions. Okay. So, you have to be careful in order to create a situation where the Na plus ion is blocked in a manner, so that its activity is also blocked, and the ion selective electrode can only specifically pick up an SO4 minus ion in the presence of Na plus ion, okay, -2 ion in case of SO4 minus 2 ion in place of or in the presence of Na plus ion. So, you have a fairly good idea about activity coefficients at this time and how they would be calculated. Okay. So, once we are actually done with this activity coefficients, what is very important to find out here is that, you know, due to these activities, what is really the change in the EMF. Okay. the measured potential of such a solution where you have about more than one species of ions with interfering ions as well as the primary ion of interest. So, essentially the E value, the potential value would change because of these participating other kind of interfering kind of ions. And there is a set of equations called Nicholas-Skye-Eisenman equation, which is used for predicting the EMF value of J such components together in in a solution, in an electrochemical solution, and the effects of those components on the measured EMF of such a solution. So, for designing ion selective electrodes, the very important factor is the ion selectivity coefficient. Okay, and so it's kind of quantification of the interference. So, in a nutshell, we can summarize all this as that ion selective electrodes respond to particular ions, and nearly all are subjected to interference from other similar ions, and the interference can be quantified, is normally provided with the literature that ion selective electrodes are supplied with. Okay, and the extent of interference is expressed by this set of equations, Nichols-Skye-Eisenman equation, as a selectivity coefficient. So, the EMF of given out by such a solution which has more than one ion of participating ions with one ion of interest and the remaining interfering ions can be also written as K plus S log of AI, which is the activity of the primary ion of interest, plus Kij, and this is called the ion selectivity coefficient. Okay, this is a measured quantity, and I will be demonstrating, I will be just showing a table which will be talking about several such values of Kij, which means that the selectivity coefficient for a jth ion, jth interfering ion for a I ion of primary ion of interest. Okay, so the I here is the primary ion of interest, and the J here is the interfering ion. So, selectivity coefficient is in the presence of J interfering ion, what would be the selectivity coefficient of J over I, the primary ion of interest. That is how the selectivity coefficient is defined, times of Aj, which is the activity of the jth ion, which is the interfering ion, divided by N by Z. Okay, N is the charge of Ai, or the primary ion of interest, and Z is the charge of the secondary ion or the interfering ion, J in this case. So, the derivation of this equation of course is not within the scope of this course, but it does give a very good, fairly good accurate estimate of the EMF, the modified EMF in the presence of a jth phase of ion which is interfering. So, if you have several such interfering species, and by the by this is again a linear equation, if you look at it pretty linear, if you do not consider this bracketed term here, or if you consider this to be just the differential concentration, it is still a straight line with an intercept and the Nernstian slope S. Okay, and when other ions interfere, that means there are more than one ions which are interfering. In that case, the equation will slightly change. Still, it will be in the Nernst equation form, but it will be modified to E equals K plus S log of Ai plus Kij, Aj to the power of N by Zaj. Again, let me reiterate here, N is the charge or the valency of the primary ion I of interest here, Zaj is the charge or the valency of the secondary ion or the interfering ion J in this case, plus Kik, A k times Kk to the power of N by Zak plus Kil Al to the power of N by Zal, so on so forth up till all the phases are covered. Okay. So, this is essentially an extension of multiple terms of the same series here that we showed before for expressing the modified EMF in the presence of an interfering ion. So, Kij, Kik, Kil etc. are the selectivity coefficients of the jth, kth, ith phase coefficients of for the jth, kth, ith ions respectively. Okay. And essentially if you look at some of the typical examples of Kij values, okay, it can be very apparently, it is really mentioned in this table 4.1 here, which talks about the ranges and selectivity coefficients of some ion selective electrodes. So essentially if you want to measure a fluoride ion, so we were talking about these different selectivity coefficients, and let me actually take you back into the slide again. So the ranges and selectivity coefficients of some selective electrodes, ion selective electrodes, are mentioned in this table here 4.1. How to interpret this table really? This here is giving the Kij value. So if you want to measure hydroxide, which is the primary ion in this case, in the presence of fluoride, the ion selectivity of hydroxide is only 0.1. If you want to measure bromine and iodine, chlorides really must be absent from the solution, so that you could measure bromine and iodine. However, if you want to measure chlorine, there is a selectivity coefficient, especially if bromides are present. Similarly, hydroxides, in the presence of bromides will offer a Kij value which is written in this table, so on and so forth. So therefore, this table really is a summary of what would be the selectivity of a primary ion of interest over the several interfering ions which are measured, which are mentioned here in this extreme left column of this particular table, and the selectivity coefficients are independently mentioned here or individually mentioned here in the third column of this particular table. Okay. Let us also look at what the interpretation of this would be. So if the Kij for hydroxide in the presence of fluorides is 0.1, it would mean that for a concentration of hydroxide 10 times higher than the fluoride, it would give a response double that of the fluoride alone. Okay. So if the hydroxide is about 10 times more than the fluoride, then there would be a response which is double that of the fluorine alone. So which is of significance, which is of some measurable significance. So therefore you are measuring, it also means that if you are measuring fluoride and if you have hydroxide, you need not bother till and until the hydroxide is about 10 times more in concentration than the fluoride is. Let us also look at one more aspect, how to determine the value of Kij, and I would like to do some derivations here. So when we were talking about the Nikolsky-Eisenman equation, the value of Kij would come from the Nikolsky equation. So let us suppose we have certain ion of interest I for which the EMF has been measured using the Nernstian equation as E1 is equal to K plus Nernstian slope S times of log activity of the primary ion Ai. When we add a secondary ions, let us say J with a selectivity coefficient Kij, E2 here can be represented as K plus S log of Ai plus Kij a to the power of, or Aj to the power of n by Z, suppose. Okay. N and Z are of course the valencies on ion I and ion J respectively. So if you just try to calculate Kij here, it could come out from subtracting equations 2 from 1, and we can get E2 minus E1 is S log of Ai plus Kij Aj to the power n by Z by Ai, right. And here this is actually the modified activity. Let us assume that this modified activity is Ai dash. Okay. This is no longer Ai, because Ai is the activity of the ion in presence of none other, and Ai dash is the modified activity of the ion in the presence of the phase J. So if we solve this equation and trying to find out what Kij is from this equation. Kij can be written down as Ai times of 10 to the power of E2 minus E1 divided by S minus Ai dash, okay, divided by Aj to the power of n by z. That is what Kij would be in this case. Ai dash, again I reiterate, is actually the modified or corrected activity of the mixed solution. So, let me write it down somewhere that in this particular case Aij, Ai dash is modified activity in presence of ion J. Okay. Since now we have more or less covered how to calculate the activity of a particular ion of interest in a solution, and also we have seen a methodology for calculating the selectivity coefficient. Now, let us do a practical example wherein we have let us say two participating solutions, okay, and we have a data of the EMF from the pure solution as well as the mixed phase, where both the solutions are participating, both the ions are participating, and we try to calculate what the Kij or the selectivity coefficient would be. So, let us look at a solved example here. Let us suppose that the for a calcium ISE, for a calcium ion selective electrode, the calibration slope S is essentially plus 29.6 millivolts per decade. This word decade essentially means one order of concentration. So, if the concentration is changed by one order, the log to the base 10 of it would be changed by exactly 1 unit, and so therefore, S essentially is nothing but plus 29.6 millivolts. It also makes sense because S is equal to, if you look at is the 59 millivolts divided by number of electrons transferred. N in this case is 2 because calcium can get oxidized to calcium plus 2 state, and therefore, in that case also the slope is plus 29.6 millivolts. So, this is essentially the calibration slope is in a 0.001 molar solution, and so in a 0.001 molar calcium chloride solution, the cell potential, okay, of while measuring through the ion selective electrode was measured to be 20.1 millivolts. Now, we mix this calcium chloride solution with NaCl or salt solution in the following ratio. So, and then measure the potential again. So, the potential in the mixed solution containing 0.001 molar of CaCl2 and 0.1 molar of NaCl, okay, was 19.8 millivolts. So, the pure solution of calcium chloride with ion selective electrode on calcium measures 0.001 molar, and the one with the mixed solution containing 0.001 molar of calcium chloride and 0.1 molar of NaCl was minus 19.8 millivolts. So, you have to calculate the selectivity coefficient of Ca plus 2 ion in the presence of Na plus. Okay. So, the selectivity of the calcium plus 2 ions in the presence of Na plus has to be calculated. In other words, if you look at the ion selective coefficient, you are essentially calculating K Ca plus 2 Na plus. This is the jth ion, the interfering ion, this is the ith ion. So, how do we calculate it? So, to begin with, we have to first calculate the activities of the calcium and sodium ions in the pure solution and the mixed solution. So, let us first do the pure solution case. Okay. So, in the pure solution, we have to calculate what gamma Ca plus 2 would be. Okay. And so, for doing that, we need a ionic strength, a mean ionic strength of pure solution and also mixed solution. Okay. So, ionic strength of CaCl2 half CiZi square. Ci here is 0.001 if it is a pure solution. okay, times of plus 2 square. The charge on the calcium, or the valency on the calcium, is plus 2, plus CaCl2. So, there are 2 chlorine atoms per molecule of CaCl2, and so the chlorine concentration would be exactly double, 0.002 molar times of minus 1 square. This comes out to be equal to 0.003 molar. Okay. So, this is the ionic strength of the pure solution, which is needed to calculate the gamma Ca plus 2 pure. Let us also calculate the ionic strength of the mixed solution, which has CaCl2 and NaCl both phases. So, we have half times of, and the concentration of CaCl2 is 0.001 molar as reported in the mixed solution, with plus 2 square plus 0.002 for the chlorine times of minus 1 square plus again 0.1 times of 1 square, 1 being the valency on the NaCl, plus 0.1 times of minus 1 square, okay, and this comes out to be effectively equal to 0.103 molar. So, one the mu for CaCl2 comes out to be 0.003 molar, and for the mixed solution the mean ionic strength comes out to be 0.103 molar. After doing this, let us find out that in the pure solution what is the activity coefficient of the Ca plus 2. So, in pure solution the activity coefficient of Ca plus 2 can also be represented by the following, okay, minus log of gamma Ca plus 2 pure, let us indicate this as pure, okay, equals 0.511, which is the parameter A which we calculated before, plus Zi square, in this case it is plus 2 square, the valency on calcium is plus 2, times of root over the mean ionic strength, which was found out from the earlier equation to be 0.003 molar, divided by 1 plus 3.3 10 to the power 7, which is also the value of the B parameter in the particular equation, into, we have to really locate what is the ion size parameter in this case, and if you just go back and look into what that parameter is, the ion size parameter for a calcium plus 2 ion, as you can see here in this case, is close to 600 picometers. Okay. So, it is about 600 picometers. So, 6 10 to the power minus 8 centimeters. Again, I would like to reiterate that all these system of equations is based on CGS units. So, we need to take the value in centimeter. So, 6 10 to the power of minus 8 is the ion size parameter A in this case, times root of 0.003 the mean ionic strength. So, this comes out to be equal to 0.1008. Okay. So, essentially taking antilogs on both sides, the gamma value, or the the selectivity coefficient of the pure Ca plus 2, okay, comes out to be equal to 0.793 as in this particular case. So, in pure solution, therefore, if we see what is the ionic activity of the calcium plus 2 ions, okay, so the Ai value for the Eisenman equation, it comes out to be equal to act Ca plus 2 pure, the gamma Ca plus 2 pure times of the concentration in this case is 0.001 molar. Okay. So, it comes out to be 7.94 10 to the power of minus 4 molar. That is what the activity of the pure calcium ions is in a pure solution. Let us simultaneously find out what is the Ai dash, that means the activity of the calcium plus 2 ions in the presence of Na plus. Okay. So, in order to do that, in the second phase of this question, we need to actually see what is the activity coefficient for Ca in the mixed solution. So, we find out the activity coefficient of Ca plus 2 in the mixed solution. Okay. So, we have in the mixed solution minus log of gamma Ca plus 2, and let us call this phase mixed phase, equals 0.511, which is the A parameter, times of plus 2 square again, because Z is plus 2 essentially, into or product multiplied by the mean ionic strength in the mixed phase, which is 0.103 as calculated before, if you remember, divided by 1 plus 3.3 10 to the power of 7, which is the B parameter, times of again the calcium ion of course has the ion size parameter of 600 picometers, which we just deciphered moment back last slide, or 6 into 10 to the power minus 8 times of root of 1.103, okay, root of 0.103. So, the gamma Ca plus 2 in the mixed phase in this manner comes out to be equal to 0.3978, and if you look at the Ai dash value, that means the activity of Ca plus 2 in presence of Na plus, okay, that comes out to be equal to essentially 0.3978 times 0.001, which is also the molarity of the CaCl2 in the mixed solution, and that is 3.987 into 10 to the power of minus 4 molar. Okay, so, that is what the mixed activity or activity of Ca plus 2 phase is in the mixed solution. So, going to the second part of the problem, let us find out what is the Aj value, that is the J in this case being the sodium plus ion or Na plus ion. The Aj value essentially is the activity of the Na plus in the presence of Ca plus 2. Okay. So, we calculate that here. So, calculating in the next phase the activity of the interfering ion. Here the Ai dash, Ai, Aj are all according to the Nikolsky-Eisenman equation, okay, which we had discussed just about 2-3 slides back. So, essentially the interfering ion here is Na plus. So, for the Na plus we have minus log gamma Na plus, okay, in the we call it mixed again because the Na plus is present only in the mixed solution, is equal to 0.511 A parameter times of Z square. Z in this case is plus 1 because Na has a Na is a univalent ion. So, Na plus is a univalent, so plus 1 square times of root of the mu, which is again it does not get altered, mean ionic strength remains same in the mixed solution, 0.103 whole under the root, and this is actually divided by 1 plus 3.3 10 to the power minus 10 to the power 7, which is the B parameter, times of the value of Na or the ion size parameter of Na, which is about 400 picometers from the table as we had done before. So, this is 4 10 to the power minus 8 centimeters, again the CGS units have to be used, root over 0.103, and this comes out to be equal to 0.11497. Okay. So, therefore, the gamma Na plus in the mixed phase or the activity coefficient of the sodium ion in the mixed phase comes out to be 0.7674, or the activity of the sodium ion ACT Na plus in the mixed phase comes out to be equal to 0.7674 into 0.1, which is 7.67 10 to the power minus 2 molar. Okay. That is what the activity of gamma of Na plus in the mixed phase is. So, this is corresponding to also Aj. So, we have pretty much everything which we need for the Nikolsky-Eisenman equation solution, and we need to find out what the ion selectivity coefficient of K Ca plus 2 is over Na plus in the mixed phase, and that can come out by the equation Ai, which is A Ca plus 2 pure, if you remember correctly, the activity of Ca plus 2 pure times of 10 to the power of E2 minus E1 by S. If you remember from the question earlier, the E2 was given as minus 19.8 millivolts, that is the potential generated by measurement along the mixed phase or the mixed solution, and E1 the potential on the pure solution was given as minus 20.1 millivolts. So, E2 minus E1 by S really is nothing but 0.3 divided by 29.6. Okay. So, therefore, this 10 to the power E2 minus E1 by S minus AI dash, which is the modified activity of Ca plus 2, that means this is the mixed phase activity, divided by Aj, which is to the power n by z, and Aj here is the activity of the Na plus mixed phase, okay, to the power of n by z. N is plus 2, mind you, because this is the valency of Ca, the primary ion of interest, and Z is the valency of the secondary ion or the interfering ion is 1, as in case of Na plus. So, if you put back all the values here, it comes out to be equal to 7.93 10 to the power of minus 4 times 10 to the power of, and you calculate this as 0.3 divided by 29.6 millivolts minus 3.978 10 to the power of minus 4, which are just these values have been all calculated earlier, if you may recall, divided by this 7.67 10 to the power of minus 2 times of or to the power of 2 by 1, okay, that is 2, and so this comes out to be equal to 0.0703. Okay, so that is what the K Ca plus 2 in the presence of the interfering ion Na plus is going to be. What really it means is that a solution containing almost 14 times as much Na plus as Ca plus 2 would give a response which is double that of the value for Ca plus 2 ions alone. Okay. So, definitely Na plus ion is a weakly interfering ion to Ca plus 2. So, in conclusion, what I would like to ascertain here is that in these kind of problems you get a very good idea or a very good feel of what would be the level of interference of a certain ion over primary interest, and this is definitely very helpful for designing ion selective electrodes. So, at towards the end of we are almost towards the end of this lecture, and I would like to discuss again what we would take up in the next lecture. So, we have now by and large seen detailed derivations about ionic activity, understood and realized the importance of how it is helpful in designing ion selective electrodes, and also how we can predict the EMF of a solution which has all these mixed phase ions of different kind with some interfering, some primary ions of interest. Now, coming to some physical some physically realizable electrodes, etc., the natural question is that can we really look at some of the sensors more closely and how the mechanisms help them to sense things like gases, or things like certain metabolites or chemicals. These sensors are often used in medical diagnostics area, where problems related to increase in urea within the blood or increase in blood glucose, etc., are quickly recorded and sent. Almost real time investigation is sometimes done on the bedside, as we have been talking out in our earlier lectures before. So, in the next lecture I would like to cover more or less some details about what is that interface of some of these sensors with the different metabolites of interest related to human body, human blood, or some other gases which may be effective for designing a gas sensor maybe eventually. And then we would like to look at how we can further miniaturize them to have an electrochemical response and understand how in a MEMS way, in a micro engineering manner, or using micro engineering tools, we could develop something sensitive to detect and pick up analytes of interest. So, I would like to close this lecture with this. Thank you.